So I believe I sent out like 30 reviews or something like that. Is that right? Yeah. So I mean, it's just a bunch of old stuff, and see how that goes to help you. Please don't ask me for solutions to all of those because it's not going to happen. But I'm happy to help you if you have any trouble with any of the problems. Just get in touch with me, text me, call me, email me, whatever.
So it's only through what today is, right? For next Thursday? Only through today?
As far as what will be on the test, yes.
Okay.
Yeah, I don't even remember what's on all the reviews. Maybe we'll look at them and I'll say, oh, you know what, we didn't get to that. Or okay, well, last time we were talking about improper integrals, right? And we were trying to come up with this idea of how we could find areas under curves if you're allowed to allow your interval to become infinite. And we did, I believe, 2 examples. And so what I'd like to do is pick up today with a 3rd example. And the example we're going to do now, why does that look like that? That's weird. Let me close that and reopen it. It looks strange. Much better. So let's look at that one right there. Yeah, sure. I don't know how healthy it is. All right, take a look at this. What I think I'm going to do first is I'm going to graph this function so that we can see what it looks like. The function is f of x equals 1 over 1 plus x squared. So there's the graph of the function. And you can see from this graph that as you go to the right, it dives down to the x-axis, asymptotically approaches 0. And as I go to the left, the same thing happens, right? And so we're asking, what is the area underneath this curve, right? If you were to go in both directions forever, that's why the integral has, as its lower limit of integration is negative infinity, and the upper limit of integration is positive infinity. So we're going to go in both directions forever. Well, last class we said, all right, we can't technically go to infinity. So what we did was we replaced the limit, the upper number with a letter. And then we did a limit. So here we have to replace both. So watch the way I set this up. To do this integral from negative infinity to infinity of 1 over 1 plus x squared dx, I'm first going to use a property of integrals that we established last class that allows me to break this into 2 integrals. I'm going to go one integral that goes from negative infinity to any number I want between negative infinity and infinity. So what would be a nice choice? 0, right? Let's go to 0. And then we go 1 over 1 plus x squared dx. We're going to figure out what that is. And then add to it the integral that picks up at 0 and then goes to the right forever to infinity. And then figure out what that turns into, right? Now remember, when we do these integrals, we're going to evaluate a limit. And if the limit exists, we get an actual numerical answer, then we say that the integral converges. If we get that the limit doesn't exist, or we get that the limit gives us infinity or negative infinity, then we will say that the integral diverges. So the question now for us is, do these both converge? Or do they both diverge? Or does one diverge and one converge? We don't know, right? All right, so let's focus on these. Let's look at this one first. What I'm going to do is I'm going to replace this lower limit of integration with a letter. And I'll use t. So I'm going to leave a space here in front on purpose. I want to go the integral from t to 0 of 1 over 1 plus x squared dx. But I'm going to want that t to head to negative infinity. So in front, I'm going to put the limit, and I'm going to let the t go to negative infinity here. So that's me rewriting that first integral. And then I say plus, and now I'm going to do this integral, and I'm going to replace the infinity with a letter. Now I could use t again, but just so that there's no confusion, I'm going to use a different letter. So I'll go with, I don't know, r, is that okay? And 1 over 1 plus x squared dx. And I'm going to take the limit this time. I'm going to let r go where? Positive infinity. There we go. Now, for each of those, I need to actually find the antiderivatives, don't I? I need to find the antiderivative of this, use the fundamental theorem of calculus, and then evaluate at the 2 points, and then do a limit at the very end. So let me set that up here. Yeah, and so you need to know what the antiderivative of this is, and you should recognize that as being arctangent, right? That should be something that you recognize at this point, that the antiderivative 1 over 1 plus x squared is inverse tangent. So I'm going to write now limit t goes to infinity. I'm going to put a bracket, trying to squeeze this in here. The antiderivative of that, we just said, is inverse tangent of x, right? And we're going to evaluate that from where to where? What goes on the bottom here? Not yet. That's going to, oh, I didn't put negative, sorry. I didn't put negative infinity here. So this is t, right, is our lower limit of integration. Our upper limit of integration was 0, right? That's this first one. Questions there? All right, next to it, plus, now I'm taking the limit as r goes to positive infinity, and then I do the antiderivative, which is the same exact antiderivative, inverse tangent of x. But this time I'm evaluating from 0 up to r. That's this integral. Understood? We're okay? All right. I should have given myself a little bit more room. I don't want to erase anything yet. Let me see if I can squeeze that in right here. Equals, okay, I'm going to rewrite this limit. Limit t goes to negative infinity of, now a little bit more room here, because when I actually do this, right, I have to first plug in 0 and then plug in t, right, and subtract. So 2 sets of parentheses. This is the kind of the standard approach when you're doing the fundamental theorem of calculus. The way I like to do it, parenthesis, parenthesis, subtraction. Plug the 0 in first, inverse tangent of 0. And then over here, inverse tangent of t. So 0 goes in, t goes in for x. Then I will add to that, now my next one, limit r goes to positive infinity, parentheses, or brackets I should say, parenthesis minus parenthesis. I plug r in first this time. So inverse tangent of r. And then over here, inverse tangent of 0. We all still good?
My only question
Yeah.
is when we did the inverse tangent, I assumed that.
That was your idea.
Okay, I'm just saying that, but like, so I'm not as good as this as you are. So I'm assuming that you already, because there's those fractions in front and after the inverse tangent. So I'm assuming
Oh, yeah. No, well,
that the x over
in the formula it's formula 17. This is a squared in the formula. For us, a is 1. Right, look, right here, it's 1. So the formula, the actual technical formula that we have for this is the inverse tangent, sorry, what am I doing? The integral of 1 over a squared plus x squared dx is 1 over a inverse tangent of x over a plus c. That's the formula 17. For us, a is 1, right?
Yeah.
So that's just 1, and that's x, which is why I just went straight to this.
That's what I think.
Is that what you're talking about?
Yeah.
Okay.
I think in your head, you should have saw that. That was like.
But before we learned 17, when we were learning about the derivatives of inverse tangents, way in the beginning of this class, we said the derivative of inverse tangent of x is 1 over 1 plus x squared. And I said, this is a really important one. So when you told me that just a second ago, I thought you were going off of that, not off of the formula.
Oh,
You can look at it either way.
Okay. That's good to know.
We're good though? Okay. Yes?
I had two questions. So the first one is that just by looking at the equation itself, can we determine if something's odd or even? And then assuming that if we know that it's even, can we use that?
Yes, you could. So the question here goes back to a property that we had last class, that if you have an even function, then you can just do half of it, like from 0 to infinity, and then double the answer. And if you had an odd function, then you can just go from 0 to, well, in this case, it would be 0 if it was odd, because they would cancel each other out. But we don't have to. I mean, we can just do this as well. Yeah. That's your first question?
Yeah,
That's
like
both?
two of them, but that
Okay.
answers them both.
All right. All right, can I proceed? Okay, let's take care of what we know here, and that's inverse tangent of 0. Now this is where things get a little weird, because it's going to depend on your understanding of trig functions. The way that I look at this is like this. If I'm asked, let me put it up here. If I'm asked to find what inverse tangent of 0 is, I do not go to my calculator and type it in, right? What I do instead is I go and I realize that this is really asking me tangent of what angle gives me 0, right? If I take tangent of an angle, when do I get 0 out, right? So I like to then go to my understanding of what the tangent function looks like, which I have to know what it looks like. And I know what it looks like because I took pre-cal and I passed it. So that's what the tangent function looks like. It has a vertical asymptote at pi over 2 and negative pi over 2, like this. And it actually continues and it repeats itself. This graph, the graph of tangent, is on your formula sheets. But you should feel comfortable with tangent just the way you feel comfortable with sine and cosine, right? So that's what it looks like. So if I'm saying tangent of what angle gives me 0, I'm saying what angle do I plug in to get 0 as an output? Well, 0, right? 0. So these, both of these, this and this one, are both zeros. So that's saying, at what angle does tangent spit out 0? Well, at 0. Tangent of 0 is 0. Yes? Okay. Now let's go to the next line. All right, I'm continuing my work here. I know that those are zeros, so I have equals limit t goes to negative infinity. And the only thing left here, right, the only thing left here, this was 0, is negative this. So I'm going to put negative tangent inverse of, I'm going to put that t in parentheses. That t I'm putting in parentheses. So I need to figure out what that is, and then add to that. Then over here, same thing, right? Well, this one went away, right? So I have limit r goes to infinity of this. And I'm going to put the r in parentheses. I should have maybe done that to begin with. It's not wrong what I put down there, but it's maybe it's confusing. We still good? All right, now we take the limit. So I look at this, and I'm going to let t go to negative infinity. So I'm looking at this, and I'm saying, what happens if that number heads to negative infinity? Well, think, what did this say? If I said inverse tangent of 0, I said, where on this is my y-coordinate 0, right? So this is saying, this is saying to me right here, where on the tangent function is the y value negative infinity? Well, you actually never get to negative infinity, but we know that the closer we get to what? Negative pi over 2, the closer this thing dives down to negative infinity, right? So in terms of a limit, in terms of a limit, the more this number gets close, the more that this number here gets closer to negative infinity, the inverse tangent gets closer and closer to negative pi over 2.
So we're plugging in negative infinity for the y value, we're looking for the x
Yes,
output. Okay.
but you can't plug infinity. I mean, we are but aren't. You know what I mean? We're saying, because you can't plug infinity in, or negative infinity. You can't plug it in. But you can see by the graph that this right here is approaching negative infinity as our x value approaches negative pi over 2. So we're looking for the x value here.
So the only thing that's weird is the negative sign in front of it. Does that turn it into a positive?
So yeah, it's going to turn into a positive. So what we have here, let me do the next line. Oh, well, let's talk about this one. What happens here? I'm letting r go to positive infinity this time, right? So I say inverse tangent positive infinity is pi over 2, right? Is positive pi over 2. So again, I'm going to run through this. This is the way my brain does this. Inverse tangent of infinity, I'm saying where on the tangent function is it headed to positive infinity? And so I look at it and say, oh, at pi over 2. So my next line, this is me doing the limits. I get over here, I get negative pi over 2, and then plus, and then here this is just pi over 2, and that's negative is positive, so pi over 2 plus pi over 2, which is pi.
So now you say it converges,
It converges to pi.
and you're expecting the converges and diverges on the test, right?
Yeah, say it converges.
Okay.
Converges to pi. It converges to pi. So what we're saying here is that if you were to be able to somehow do it, where you look at the area underneath this graph, that the further out you go, right, the closer and closer you get to pi. But you'll never go past pi. No matter how far you ever go, you just get closer and closer to pi. And remember, pi is a irrational number, right? It just goes on forever. So you're just going to keep getting more accurate estimations of pi if you go further and further. Yes?
Just gonna ask if that was just a regular tangent,
If this was regular tangent,
instead of tangent inverse,
how
would you use that one? So,
you couldn't, because the limit wouldn't make sense, because as you go out to infinity on tangent, you keep on having asymptotes, yeah. So,
do not exist.
yeah, does not exist. Yeah. It's not going to happen, though. So, yeah.
So is the integral of 1 over 1 plus x squared equivalent to pi?
Only between negative infinity and infinity. So you could say that. If you wanted to, if someone said, hey, what's pi? Someone could say, oh, well, one definition of pi is that you take a circle, you take its circumference, you divide it by its diameter. That's a very clean definition of pi. Draw me a circle, whatever the circumference is, take that, divide it by the diameter, and that's the definition of pi. Another definition of pi is the area underneath this curve between negative infinity and infinity. That is a second way that you could define pi. Absolutely. It's like you could write the number 1 in like infinitely many ways. There's an infinite ways to write pi as well.
So the whole point of us doing the way we did was we used self-equivalent letters, but we couldn't do two different letter variables in one.
Yeah, exactly. We need to do 2 different limits. And so we need 2 different letters, so we split it up.
And that's fine as long as like you make it like a continuous type of thing.
Yes, as long as you go from like negative infinity to a number. I could have gone negative infinity to 10, 10 to infinity, but 0 just was natural. And it actually worked out nice because when we did inverse tangent of 0, it was 0, right? Okay, understood? Next one. Negative infinity to infinity. X e to the x. So there's a lot of different ways that you can start thinking about this. One thing you could do is say, oh, look, I've got negative infinity to infinity. I'm going to need to split it into 2 integrals. One goes from negative infinity to 0. The other goes from 0 to infinity. I'm going to split this up. You could start going down that road. Or you could say, you know what? I'm going to need an antiderivative at some point, right? And maybe I should do that first, like figure out the antiderivative, because I'll need it later. Totally up to you. This antiderivative is not as easy as the last one. The last one we just kind of said, oh yeah, 1 over 1 plus x squared, inverse tangent, formula 17. This one is going to require what? By parts, right? We're going to need some by parts. So why don't we go do that first on the side? Like, let's just go figure out what the antiderivative is on its own. This is kind of like my little scratch work over here. I just need to find the antiderivative of x e to the x dx. So I'm going to do an integration by parts. See, no definite integral, no limits of integration. I'm just doing our old school, let's find the antiderivative. So I make my table. U is going to be x. dv is going to be e to the x dx. The derivative of u is dx. And the antiderivative of e to the x is itself. I'm going quickly through this because we've already done this before. So ultraviolet minus the integral of voodoo, and then that's ultraviolet minus the antiderivative of e to the x is itself plus some constant. So that's just me finding the antiderivative. I'll use that in a moment. Let's now get back to this. That is equal to the integral from negative infinity to 0 of x e to the x dx plus the integral from 0 to infinity of x e to the x dx, which is equal to the limit as t goes to negative infinity of the integral from t to 0 of x e to the x dx plus the limit as r goes to infinity of the integral from 0 to r of x e to the x dx. All right, that's just me writing everything that we just did on the previous problem. I split this into two integrals, from here to 0, then from 0 to there. And then I'm going to replace this with t, and then do a limit and let t go to negative infinity. And then replace that with r, and let that r go to infinity. Good or no? Yes? I know, I wrote that really quickly. Now, this one's dead. Okay, I'm going to try and put this in trash can. I'm 0 for 3 today. 0 for 4. I'll just leave it right there. Leave it right there. All right. So now I'm going to write limit. First one, t goes to negative infinity. All right, bracket. Okay, I need the antiderivative, right, which I already did. So the antiderivative over here was x e to the x minus e to the x. And I want to evaluate that at where to where?
Infinity to 0?
T to 0. T to 0. T to 0. Plus limit r goes to infinity of the antiderivative evaluated from where to where? R to infinity. 0 to r. Careful. You got it though? Yes? Yeah? Okay. You get it. All right. Everyone understand where those are coming from? Right? We went from t to 0, so this is going to go from t to 0 here on the antiderivative. We went from 0 to r, so our antiderivative we got to evaluate from 0 to r. When I say evaluate from something to something, I'm always imagining myself moving left to right on the number line, right?
So, just to clarify this, so when you're substituting the t and the r and all that, how are you deciding where the b number, say, is 0 in this case? Like if it goes on top or
Well, that's what I'm saying. Think of a number line, right? Here's negative infinity, here's infinity, right? We split it at 0, didn't we? And then we said this is going to be, instead of infinity, this is t, right? And then instead of this, we're going to say r, right? So your first integral should go from t to 0, and then your next integral should go from 0 to r, 0 to r. Yes? What's up?
is there any reason why you use brackets?
No.
It's easy to write when
No, I just, I don't know. I mean, like, later on, when I was a student, I used brackets. Later on in math, I didn't use brackets as much. Because parentheses and brackets are equivalent. So, but most textbooks will use brackets most of the time. But there's nothing wrong with the parenthesis there. Okay, so now what I'm going to do is actually do these plugins. Negative infinity. So bracket here. Parenthesis minus parenthesis, like that. Okay, so that's going to be the setup for this one, right? I'm going to let t go to negative infinity. I've got to plug 0 in here and then subtract from it what I get when I plug t in here. Then I'm going to do the same thing over here, right? R in here and then 0 in here. So I have another limit after this. R goes to positive infinity. Parenthesis, parenthesis. I don't know if I'm giving myself enough room there. We'll see. Okay, what happens when I plug 0 into this? That's 0, right? That's 0. 0 times e to the 0, so that's 0. E to the minus e to the 0? Negative 1. Negative 1. So I get negative 1 here. And then when I plug, what do I plug in? I did that first, then this, right? When I replace all my x's with t's, I just get just t's where the x's were. That's it, right? So it's going to be t e to the t minus e to the t. Sorry, it's crammed in there, but yeah? What's up? Are you lost? Okay, I'm doing this right here. The fundamental theorem of calculus says that to do this, we have our antiderivative is here. We first plug this in. So you're okay with where we got negative 1? And then I subtract from that what I get when I plug t into this. So t, t, t. That's it. Now I'm still going to have to do a limit in a little while, but I mean that's where I am at this point. Now I'm going to move to this one. So I'm about to do this setup right here. And to do that, I start out by plugging r in first. So it's going to be the same expression with r in it. I'm going to give myself a little more room. So if I plug in r, I get r e to the r minus e to the r. So that's r going in. And then what happens when you plug in 0? Negative 1 again. Everyone okay?
The way you got negative 1 is just like 0 is that last part it's going to just go to 0.
That's 0 times who cares, right? Well, e to the 0 is 1. E to the 0 is 1. So 0 times 1 is 0. Minus e to the 0. E to the 0 is 1, so minus 1. Any others? All right. Now it's time to deal with these limits. So the last limit we did involved the inverse tangent, and I had to go look at the graph and try and figure out what's going on. Here, I've got something else happening. Let's start with this. I want to know what happens when t goes to negative infinity of that expression right there, right? Now, so that we don't screw this up, I'm going to do some scratch work over here. Okay. What's the limit as t goes to negative infinity of t e to the t minus e to the t? All right, let's take our time through this. Don't rush it, because students will just tell me, oh, this is 1, or oh, this is 0, without any evidence at all. All right, let's see if we can convince ourselves of what this is. So t is getting really big but negative, right? So where do we start? Let's start here. Where does this go then? If I tell you that t is going to get real big and negative, then that's going to negative infinity, isn't it? So it's going to be a negative, big negative number. Okay, good. Where does this go? Be careful. 0. Why?
Because the exponential function approaches 0.
Yeah, so you have to know what the graph of e to the t looks like. You have to actually know what it looks like. So what does e to the t look like? I'm out of room. Okay, e to the t, well, e to the x. Let's look at e to the x. That's what we're used to seeing. E to the x looks like this. How do you know that? Because you passed college algebra, right? So e to the x looks like this. And what I'm doing is, the x is the input, right? So this is your x. If we go this way, it's positive infinity, right? If we go that way, it's negative infinity. So we want to know what happens if I try and replace that right there with negative infinity. Well, that means go this way. So where is that headed? To 0, right? It's headed to 0 there. Hold on. So this is headed to 0. Agreed?
Yeah.
And then minus, what is that headed to? The same thing, right? That's e to the negative infinity heads to 0 as well. Right? That's what's happening. No, it's not 0. Hold on. Did you have a question or no?
Yeah, it's not like a property of e to the x that's like that. It's just any constant to the power of x that creates that shape.
Okay, so the question here is, does this work for any number down here? So you're saying, what if we had like a to the x? Does this work like this? The answer is only if a is greater than 1. If a is between 0 and 1, then it flips over the y-axis and you have exponential decay instead of growth. So your graph actually looks like this. But e to the x is the one that matters right now. Pardon me?
You could also just do it algebraically with negative exponent. That's the way I would.
Yeah. So you could also think, okay, if I'm doing e and that's a negative number, right? Then that's the same as 1 over e to the positive number, which becomes infinitely big on the bottom, and 1 over an infinitely big number heads to 0. Okay, so there's 5 different ways to look at this. Yeah, and some people, their brains work better that way. Some people, they like the graph. It depends on you. But we should all get the same answer, yeah.
I have a question.
Yeah.
Do you have to know what the graph looks like, or can you just plug in the t, e to the t minus e to the t in the calculator, just look at the graph?
What are you going to plug? Oh, you look at the graph from, you mean to actually just plug that whole thing in and look at the graph?
Yeah.
Well, yes and no. I mean, you could, yes. That would give you a result. Most of the time, you should be able to look and see. But that kind of circumvents the whole idea of what we're doing here, because then you're depending on technology to answer your question, right? Okay. If that were the case, then we would have just done this integral with technology to begin with, right? I just go to like Wolfram Alpha, I type in the integral. You can use infinity in Wolfram Alpha, and it'll give you an answer. So what we're trying to make sure is we understand, this is called number sense. It's us understanding how numbers are working together. That's a way bigger idea that we're trying to kind of get comfortable with in a class like this in Cal 1 than the idea of using a tool. So does that?
Yeah.
Yeah, okay. All right, so now we're looking at this. This goes to 0, minus 0, not a problem, right? This is, I'll use a different color. This is happy, okay? That goes to 0. This, on the other hand, is not happy, because in Cal 1 we learned that if you have a number that's getting really big and you multiply, not times 0, is this number ever 0? No, it's just a really small number. So you have something that gets really big times something that gets really small. What happens?